By the 1930s, Einstein's quest for unification was floundering, while quantum mechanics was unlocking the secrets of the atom. Scientists found that gravity and electromagnetism are not the only forces ruling the universe. Probing the structure of the atom, they discovered two more forces. One, dubbed the strong nuclear force, acts like a superglue, holding the nucleus of every atom together, binding protons to neutrons. And the other, called the weak nuclear force, allows neutrons to turn into protons, giving off radiation in the process. At the quantum level, the force we're most familiar with, gravity, was completely overshadowed by electromagnetism and these two new forces.
Now, the strong and weak forces may seem obscure, but in one sense at least, we're all very much aware of their power. At 5:29 on the morning of July 16, 1945, that power was revealed by an act that would change the course of history. In the middle of the desert in New Mexico, at the top of a steel tower, about 100 feet above the top of this monument, the first atomic bomb was detonated.
It was only about 5 feet across, but that bomb packed a punch equivalent to about 20,000 tons of TNT. With that powerful explosion, scientists unleashed the strong nuclear force, the force that keeps neutrons and protons tightly glued together inside the nucleus of an atom. By breaking the bonds of that glue and splitting the atom apart, vast, truly unbelievable amounts of destructive energy were released.
We can still detect remnants of that explosion through the other nuclear force, the weak nuclear force, because it's responsible for radioactivity. And today, more than 50 years later, the radiation levels around here are still about 10 times higher than normal. So, although in comparison to electromagnetism and gravity, the nuclear forces act over very small scales, their impact on everyday life is every bit as profound.
But what about gravity? Einstein's general relativity, where does that fit in at the quantum level? Quantum mechanics tells us how all of nature's forces work in the microscopic realm, except for the force of gravity. Absolutely no one could figure out how gravity operates when you get down to the size of atoms and subatomic particles. That is, no one could figure out how to put general relativity and quantum mechanics together into one package. For decades, every attempt to describe the force of gravity in the same language as the other forces, the language of quantum mechanics, has met with disaster.
You try to put those two pieces of mathematics together, they do not coexist peacefully.
You get answers that the probabilities of the event you're looking at are infinite. Nonsense. It's not profound, it's just nonsense.
It's very ironic because it was the first force to actually be understood in some decent quantitative way, but it still remains split off and very different from the other ones.
The laws of nature are supposed to apply everywhere. So if Einstein's laws are supposed to apply everywhere, and the laws of quantum mechanics are supposed to apply everywhere, well, you can't have two separate everywheres.